First thing you're going to want to do is define the problem in this bridge building contest. And the problem is it's given to you. You're trying to design a bridge that will hold the most weight with the least amount of material and span a 30 centimeter gap. We need to do background research, specify the requirements, brainstorm, evaluate, and choose solution, develop prototype solution, test the solution, and then if it doesn't meet the requirements, you go back through that process, brainstorm, evaluate, and choose the solution, develop the solution, and test the solution, and you keep going through that again and again until it starts to work. Until you get, it says solution meets requirements partially or not, solution meets requirements, then we communicate results. So we're going to be going through this engineering process here when we're building the bridge. First, let's look at some of the ideas and physics concepts behind building a bridge. I'm going to go back here to some of the forces that will be involved. The first one that's going to be involved in building a bridge is tension. Tension is the stress that's applied to something as it's pulling something apart. So you think of like a rope. When you pull on a rope, you apply tension to the rope. Solid pieces can have tension as well. That would be where stress is applied that way on an object. Then we have compression. Compression is just the opposite, where we would have an object like this, and the forces would be applied that way. You could also think of it like a pillar, and you put a weight on top of it. Weight on top of the pillar, it has compression on it because it's being pushed down by gravity, and then the Earth is pushing up on it. So we have compression on that pillar right there. So that would be compression. And the last one is you don't hear about as much as shear. Shear forces are where you have one force going this way and one force going this way. And so basically they're pushing opposite directions of each other, but not at the same point. So you could kind of think of it like if you have a stick like this, and one side is being pushed like this, and one side is being pushed like this, and it's being held in place as those two are pushed, you're putting a shear stress on that. That would be a shear force on that one. So those are the forces that are going to be involved with our bridge, and we're going to want to evaluate those and use the engineering process. What we're going to do now is I'm going to design for you a simple bridge, the simplest. The idea is you want the bridge to be as light as possible but hold as much weight as possible, because it's going to be the mass held divided by the mass of the bridge to get your score. So the bridge is going to need to cover this 30 centimeter gap, and the simplest bridge design that you see around is something like this. And then you have the triangles, because triangles work really well to make something strong, except for you would want them actually attached. So that's your simplest bridge. We could look at some of the design there. Sorry, those are supposed to be attached there. We could look at some of the stress and strain that might form. What's going to happen is I'm going to put a rod through the middle of the bridge right here, and then I'm going to hang, there'll be a wire from each side of that rod, and then we'll hang a mass down here. It'll be a little hook and a weight thing at this, and we'll hang that, and we'll keep stacking more and more weight on there until it actually breaks. So it goes through the center of the bridge, and then we put the mass on. So as we put that force on it right there, or we can do another thing, as we put the force on it right there, that's going to cause a few different stresses on this bridge. First off, if we look at it, so it's going to pull down, it's going to cause some tension right here and right here. So we'll mark all the tension in blue. Cause tension right there and right there. It's also probably going to cause some tension. Let's see where else. It might cause some tension right here and right here as it stretches it down. And right here, probably also tension. There's going to be compression on the bridge it experiences as well. So as it pushes down, you know, the compression is going to be right here, because it's going to pull the bottom, kind of stretch the bottom out, and it's going to push in at the top. We're going to get compression there and there and there. And some other places we might experience some compression. Probably not too much, but those are probably the main areas where we would need to worry about compression. And shear, we shouldn't really experience much shear stress on this. But what I would do is I'd design my bridge, and you can get any 30 centimeter gap and then test it. Use some spaghetti and glue. It has to be regular, normal size spaghetti, no other noodles, and glue, and hot glue, just regular hot glue. And you can test and you can see where that tension and that compression will be. So where you'll see those stresses on the bridge, and you can adjust and add more reinforcement in the areas where it's experiencing more stress, and then get rid of the reinforcements to get rid of weight in the areas where there's very little stress. As you can see right here, we're going to have stress in different areas on the bridge. So make sure you think through that design process and what's going to happen there. And then make sure you use the engineering process in there. So after you've developed a prototype, you test it, and then you're going to see if it meets the requirements or not, and then go back to brainstorm, evaluate. Evaluate would be to see where those strains and stresses were, and rebuild. And then we'll go from there. One thing you'll probably find is that spaghetti has very good tensile strength, meaning it's very good for tension. You can pull on it all you want. It does not break very easily by pulling on it. When you put a little bit of compression force on it, so when you pull on spaghetti, it doesn't do a lot. When you put compression force on it, it snaps almost right away. And the longer the piece of spaghetti, the less compression force it can withstand. So you're going to want short pieces of spaghetti in the areas where it'll experience compression. You want the longest pieces possible in the areas where it will be experiencing tension. So now your task is to go design a bridge and build it. I will want you to share what your bridge looks like eventually. So you're going to share a video or a picture of what your bridge looks like, probably sometime next week or the week after, depending on how long this isolation lasts. We'll evaluate based once we figure out more about the timeline. We're most likely going to test these in early April, or as soon as we do get back together, or if we get back together. If not, we might have to test them at home, and you'll send in the video of you testing it yourself, and we'll do a contest based on that. So we'll see what happens, but just start building your bridges after you've done section 1 and 2, and make sure you post to the comments as well in the discussion section.